I want to present innovations from the ViWA project. It's about virtual water values. And I will talk a lot about potentials that you have from remote sensing data, which look, at the first sight look very far away from what we heard before in the Sudan, where we really show the problems on the ground. It was really impressive. But I hope I can also show you that with the satellite data, we can also help to get solutions for problems on the ground. So our task at the ViWA project, we are the remote sensing partner, we are a private company. Our task was to analyze satellite data of the agriculture areas distributed all over the globe. So we decided not to do a complete mapping of all the agriculture areas, but do it in a very much detailed in 10-meter resolution, but distributed in more than 150 tiles over Europe, over the globe. And that you can see that these cover really the different heterogeneous agricultural landscapes on the world, which are quite different. And that was one of the lessons learned that we had as in my company, that we learned how variable these agriculture systems can be, that we learned how to parameterize and model them. Altogether, we had to process 100 terabytes of satellite data and extracted information from this relevant for hydrological purposes and also for yield forecast. What we did then on each of these tiles that we have, each have 100 by 100 kilometer, the first step is to classify the agricultural crops there. Here, for example, we have wheat, spring wheat, and winter wheat. And based on this classification, we selected representative fields. You can see the little points in the fields, and we say, okay, let's start the further analysis on these samples. It was necessary because we had 100,000 of samples already, and when you do then detailed modeling of their water needs, water consumption, water use efficiency, you have to reduce the data set, and can you do it on a 10 by meter pixel basis at present at least. Although we already used a lot of computation resources. What is the outcome of it? For each of the tiles, we have done the classification and derived typical phenological development of these crops. Here is shown all the pixels of, for example, maize, soybean, spring barley, and so on for a tile in Northern America. And here are the similar shown for regions in Europe, Africa, and Asia. So we get the information about how the crops develop in each of the tiles. Hoppla, that was too fast. In each of the tiles, and extract the information on how the crops grow there, what is their typical phenological development. And this is then assimilated in the crop growth model ProMed that is developed in the ViWA project and is run globally. And what we learned with this was, for example, that we moved to crop types that we were not we had no knowledge before, like groundnut in Africa or in rice in Asia, where we have now a 2-season crop there. We assimilated this information from satellite data now in the water balance and crop growth model ProMed. What we retrieve from this is the pixels shown here, that is our sample pixels for maize in the Danube catchment. So we can really study here how much evapotranspiration do these pixels, these samples, realistically needed in 2020 all over the Danube catchment. And there was really maize grown in all of these pixels. But we also retrieve information on the yield based on the simulations and the satellite observations. Here you see the patterns of yield that we simulated, which are also, again, very variable. When you're combining these two, we come to the variable that is most important for the ViWA project. It was water use efficiency. And you can see it changes a lot from west to east. There is mostly a reduction of water use efficiency, but also very specific and typical patterns are there, regionally very heterogeneous. And these can then, for example, be analyzed country by country. Let's look at the water use efficiency for the countries along the Danube going river downwards. We start in Germany. You can see here we not have only classified maize here, but we also selected for these maize fields whether they are irrigated or not. The dark blue ones are the irrigated maize pixels. When we move to Bulgaria downstream, you see there are much more dark blue pixels, so much area is irrigated in case of maize. And you see what this means for the water use efficiency if you see here the line between yield and evapotranspiration. So that is a very detailed analysis that is possible now using up-to-date data of also larger areas. This information, what we learned here, how to do the sampling methodology, how to do the classification, how to assimilate it in the growth model and simulate yield, this was now used also for other activities of VISTA. And with this knowledge, we developed a yield prediction system based on satellite. It's called Ypsilon. And this is now operational since 2020. It gives the forecast of yield for all over Europe. You can either select whether you have a countrywide level, as shown on the left side, or whether you have a very detailed regional product, like here Landkreis level in Germany. And we deliver yield forecast already 8 weeks before harvest with a very good accuracy. The validation of the accuracy is shown here for the last 3 years. We compare our forecasted yields with the one from European statistics. And you can see it compares very well for maize, rapeseed, and wheat. That are the crop times that we deliver so far. And you also see one of the forecasts we provided. It was the wheat harvest in Germany 2018. When you remember, that was in the presentation this morning, we said the seasonal rainfall forecast didn't see the drought in Germany. Of course, we also couldn't see it in spring already, in March or so. But if you have a careful look on it, it was end of May that we said we have a severe reduction of wheat yield in Germany, which came true at the end. Because we have the water balance model, we knew about the soil water storage in the soil, and we saw at the vegetation development that something goes wrong, so to say, in easy words. Our forecast was much earlier than the market average estimate, which is based also on a lot of field survey. So we really succeeded weeks before the others, 6 weeks before the others, to say that the yield is lower than expected. So this service now is an open service. It's a commercial but open service, and we are expanding it next year to Ukraine and Russia. That will also be available. Another application that we developed based on the results of ViWA, we learned how also agriculture in Africa works. And so we applied it for a Zambian commercial farm, which had problems in irrigation. So they had really a drop down of the reservoir levels, and we helped them to reduce their irrigation amount on their fields by delivering exactly the crop water demand that the crop needs per day. And this in a device that is shown here sector-wise, that he can optimize his pivot regulation, that it really fits the needs of the crops. And this we do for the whole season, giving weekly updates how he should irrigate. And as a result, we had 30% of reduction of water. We really could save water here. We could also save energy with this because we need pumps for the irrigation. And at the same time, yield was never decreased. It even increased partly by 25%, because often farmers tend to irrigate too much, which is also not good for the crop. So we really could improve the yield, the water use efficiency for the farm. And this is now an operational service that we apply already at 6 countries on the globe. And our partner with this is the ViWA, who are distributing it as a trade market variable rain. So you see, we can really make a lot of very down-to-earth services based on our satellite data and simulation, and based on the results of the ViWA project. Okay, thank you very much.